In this video, we're going to talk about linearization and a little bit of differentials. Find the linearization or tangent line of the following functions at the points indicated. Okay, so remember for every tangent line we need a point. So for us, x is -1. We plug -1 in, e to the -2nd. We also need the slope. Well, to get the slope, we need the derivative. So f prime would be e to the x minus 1 multiplied by the derivative of x minus 1, which is just 1. So we plug in -1, and we get a slope of e to the -2nd. So our tangent line would be the slope, x minus the x-coordinate, plus y-coordinate, like that. Next, we need a point. Well, we know x is 10. We plug 10 back in. We get the natural log of 10. We need a slope. Well, f prime, derivative of natural log is 1 over x. So, for us, the slope would be 1 over 10. My tangent line, 1/10 x minus the x-coordinate plus the y-coordinate. And that's it. Those are the linearizations of those functions at the points indicated. So I'm going to show you again how we can use linearization to estimate some functions that are hard to do. So I'm going to estimate 15.97 using linearization. So I've kind of given you some ideas here of things you got to kind of look at. You got to start by saying, well, what function am I trying to linearize? And the answer is the square root of x. Okay, and if you think about this, let me quick sketch this picture. If you think about the square root of x, looks like that. What I'm trying to do is find a tangent line at a certain x value, such that for points around that x value, the tangent line and the function are really similar. And I'm going to try and exploit that tangent line, or that relationship between the tangent line and the function, to estimate the square root of 15.97. So now you have to ask yourself, well, what would be a really easy place to evaluate the function such that I could then use the tangent line to estimate the square root of 15.97. Hopefully you can see that it's got to be 16. Okay, that if we made the tangent line at 16, because I know what the square root of 16 is, I could easily use that tangent line to estimate the value of the square root of 15.97. Okay, so let's make our tangent line. First, we need a point. Now, I know that the x is 16. So y would be the square root of 16. It would be 4. And the slope. Well, going back up here, if we could rewrite the square root of x as x to the 1/2. So the derivative, y prime of that, would be 1 over 2 square roots of x. Right? It would be 1/2 x to the -1/2. So now if I plugged 16 into the derivative to find the slope. Square root of 16 is 4, so 1 over 2 times 4. Slope is 1/8. So that means my tangent line is 1/8 x minus the x-coordinate plus the y-coordinate. Okay, so this is my tangent line. So again, what I have just done here is I've created this situation where I have a tangent line that mimics the square root function, and for values really close to the point of tangency, and again, the point of tangency here is 16.4, right? That's the point of tangency. For values very close to that, I should be able to estimate the square root function with the line because they're so similar. So let me do that. I'm going to evaluate my tangent line at 15.97. So I have 1/8 multiplied by 15.97 minus 16 is 4. So I have 1/8. Now, 15.97 minus 16 is negative 0.03. I'm going to write that as negative 3/100ths. So 1/8 multiplied by negative 3/100ths is negative 3/800ths plus 4. Well, I could rewrite the 4 here as 3,200 over 800, so we have a common denominator. So I add them together, and I get 3,197 over 800. Now, I would encourage you to type this into your calculator and also type in the square root of 15.97 and see how close they are. I believe that that is accurate to the 10,000ths place. Now, the reason it's so accurate is because 15.97 is so close to the point of tangency. If I was estimating the square root of 15, of course, the further away I get from the point of tangency, the further apart the line and the actual function are. So, I wouldn't use this line to say estimate the square root of 24. I would have to make a new line centered around the point 25 and 5. So it really comes down to picking the right point. Okay, and of course, in this case, it was obvious. This is so close to 16, and that's something we can evaluate in the function very easily. Finally, kind of along with this is the idea of differentials. The height of a triangle is fixed at 4 centimeters. Use differentials to estimate the change in area if the base is changed from 5 to 5.1. First of all, I should just point out, how is this different than a related rates question? I guess the simple answer is that there are no rates given. Nothing here is in terms of time. I'm increasing from 5 to 5.1, but it's not in going up by 0.1 centimeter every minute or something like that. So there are no rates. So without that, I don't need a d something over dt. So what I have here is, I want to know the area of a triangle, so 1/2 base multiplied by height, but I know that the height is 4. So area is just 2b. So as I find the derivative, and keep in mind now, we're looking at how it changes with respect to the base, so we're back to doing dA dB, because it's not a related rate. We're not doing dt's. Well, the derivative of 2b is just 2, period. And again, you don't need to do, we did this with respect to b, so you don't need to do dB divided by dB, because that's 1. Now, how I always think about this is, we're saying the area changes with respect to the base at a rate of 2, okay? Change in area with respect to base is 2. Well, this is change in area, this is change in base. I know what the change in the base was. It was 0.1 because my triangle increased from 5 to 5.1. So I can write this as dA divided by 0.1 equals 2. Multiply both sides by 0.1, and the change in the area I would estimate to be 0.2. Now, if you type that in your calculator, if you actually figure out the area with a base of 5 and the area with a 5.1, you find out it is exactly 0.2. Again, this is just an idea of kind of verifying some geometry ideas with calculus and looking at how things change with respect to each other. But it is different than a related rate because that was with respect to time.